voltage source is connected with all these three elements. Okay, so what will be the total impedance of this circuit? The total impedance, if we will calculate, that will be the sum of the impedance of resistance, inductance and the capacitance. Okay, so that will be equals to R plus jXL. XL is the what? This is the reactance of the inductor, and this is the Xc is the reactance of the capacitor. Okay, R plus jXL minus jXc. I think you all are familiar with these things, right? The impedance, how to calculate the total impedance, and what is the reactance. Okay, so that is I'm not explaining it in depth. So total impedance is equals to Z plus JXL minus XC, right? This is the conjugate, sorry, this is the imaginary portion and this is the real part of this impedance. So if we take the mod of this impedance, this reactance, the total reactance will be XL minus XC, okay, and the total impedance will be given by under root R square plus X total whole square, okay, and the phase angle will be calculated as given here. Theta equals to tan inverse X total means the imaginary portion upon the real part. So this is the impedance and the phase angle of RLC circuit. Now, if we analyze this circuit, the reactance of this circuit. So, when Xc is greater than XL, okay, when Xc means our capacitor value, capacitance is dominating. Xc means reactance of capacitance is greater than that of inductance. Then we will get this kind of curve for reactance versus frequency plot. Okay. And for inductance, if our inductive reactance is greater than the capacitive reactance, then we will get something like this straight line. Okay, and this meeting point of these two reactance graphs, where XL will become equals to XC, this frequency is the resonant frequency. Okay. So I will tell you what we mean about the what do we mean by the this resonant frequency. Okay, so here if we see the phase, we can see that the inductor voltage and the capacitor voltage, they both are always 180-degree out of phase with each other. Okay, this is a very important thing, that inductance and capacitance, they are always 180-degree out of phase with each other. Okay, XL and XC are given by these equations. So in series resonance, what happens? I have just shown you that XL becomes equals to XC, right? Both the reactances are equal at that particular frequency. So at that frequency, what happens, since these both are in out of phase, right, and their magnitude is equal, so what will happen? They will cancel out each other. Okay, just like this. At resonance, this VL and VC means the voltage across the inductor and the voltage across the capacitor, their magnitudes are equal and they are also 180-degree out of phase with each other. So what will happen? You can see like here VC is going from like this and VL is going, means it is starting from negative to positive and VC is positive to negative, right? So when we have applied that frequency at which the reactance of both of them is equal, then they will cancel out each other and our circuit will look like this. Okay, there will be no reactance. Reactance will be equals to 0. All right. So our final VL by VR, if we will plot, then this will be like this. Okay. So this happens at the resonance frequency, that frequency at which the inductive reactance becomes equals to the capacitive reactance of series RLC circuit. That frequency is known as the this resonant frequency. Okay, and if we will put XL equals to XC, we can easily calculate this equation for resonant frequency. It is given by 1 by 2 pi under root LC. Okay. So what is the application of this resonant frequency or application of this RLC circuit at resonance? So this is the application. The band pass filters, this RLC circuits are used. How? Because if we have connected them in this way, the capacitance means the reactances are connected here and the output is being measured at the resistor, right? So what will happen? This circuit will work like a band pass filter. Okay, the band pass filter will allow the signals at resonant frequency and at frequencies within a certain band to pass through the from input to output, and others it will stop. This will be the frequency response for this is here it is frequency versus I or V out. Anything if you will measure, then if you will plot the gain of this either voltage or current, it will be like this. Okay, so this is the curve for gain versus frequency. Okay, and this is my dear students, this is the pass band. This the frequencies which are lying between F1 and F2. Only these frequencies will pass through the circuit, through means from input to output, and the other frequencies will be stopped. All right. So this F1 is known as the lower cutoff frequency and F2 is known as the upper cutoff frequency. All right. And the 3 dB gain will be calculated by this. Suppose this gain is 1 and its 3 dB down gain is 0.707 as we calculate in every other circuit. Okay. Now what will happen if we measure the output at this point? Means across the inductance and capacitance. So the this gain versus frequency plot will be just opposite of what was there for the band pass filter. So what will happen? Our gain versus frequency response will be like this. And now what we can say? We can say that the reason between this F1 and F2 will be cut off. Okay, so the output, we will not get the output within this range of frequencies. So this is known as a band stop filter. Okay, so this band of frequencies will not get will not pass from input to output. Okay, so these are the two applications of this series RLC circuit. All right. So, okay. So today's experiment, according to today's experiment, you have two aims. First is you have to obtain the frequency response of a series RLC circuit. Just pick up any this resonant frequency, and then you have to obtain the frequency response of a RLC circuit, series RLC circuit. Okay, and you have to actually design, right? You have to pick up the inductance and capacitance values of your own. Okay, and suppose the resistance value I think is given in your this manual. It is 100 ohms, or you may take your value of your own. Okay, no issues. So you have to design a RLC circuit, then you have to obtain its frequency response. What is frequency response? It is a gain versus frequency plot, right? Then the second aim is you have to determine the resonant frequency in a series RLC circuit, and then you have to compare it with the expected resonance value. Okay, the theoretical value and practically what you are getting. Okay, so the aim is clear to all of you? Aim is clear? Are you listening to me?
Ma'am, practical value you will get from frequency response, right?
Yes, yes.
Yes, ma'am.
from the
Yes.
frequency response.
Yes.
Okay. So any doubt in this? Any doubt?
No, ma'am.
Anyone?
No, ma'am.
Others? Other than Harshvardhan, others, why don't you reply? Okay. Let's start the experiment, and those who have not shown me the last two experiments, you may show it to me today also. Okay. So first start doing this experiment. Once you complete this experiment, then only you can show me the previous experiments and this experiments in one go. Okay. So please start your experiments. I think by now all have installed the multisim software, right? Is there anyone who has still not installed the multisim? Is there anyone? Please respond to me. Is there anyone who has still not installed the multisim? Deep Rishi. Deep Rishi, are you sleeping, Deep Rishi?
Before that, ma'am.
Okay, okay. Positive reference. Then this is positive clipper with positive reference. Okay. In here, you have to just change the direction of diode. It is
Yes, ma'am.
negative clipper with positive reference and the positive clipper with positive reference. Okay. So only the direction of diode will change.
Yes, ma'am.
Okay.
visible, ma'am?
Yes, it is.
So, ma'am, I took the frequency at 500 hertz. Okay,
Hmm.
and accordingly, V peak to peak was 10 volt, right? So
Hmm.
then I calculated VRMS by VPP by 2 root 2, then it came out to be 3.535. Okay,
Hmm.
and I assumed I have to assume either capacitance or inductance. So I thought better to assume capacitance. So I assumed it as 1 microfarad. And
Okay.
since it is irrespective of resistance, I took it as 100 ohm, right?
Hmm.
So then I calculated the um, frequency in the board plotter. I checked out, then it came out to be 500 point something, and I took it as 500 hertz, and accordingly I checked it from that frequency response also, so it came out to be
Okay.
500 only. Here 500.989.
Okay. Why are you all are taking it as 500 hertz only?
Yes, ma'am.
Why you all are taking it as 500 hertz only?
We could take anything, but since I assumed it only 500, ma'am. Actually, I saw in the PDF also there it was stated to take 100 hertz. Means it just stated means it was just said to assume anything. So I took it as a 500 hertz. And since already Harshvardhan also
Ma'am,
calculated, so the result also came out to be approximately 500. So I thought it better to calculate at 500 only.
Okay.
ma'am, if you want, we can change to the frequency. There's no problem in that because it will only change the calculation. It will remain the
Yes, it
same.
will
Mm-hmm.
change that
Yes, yes.
calculation 1 by 2 pi root LC, nothing else.
Yeah.
Yeah, yes,
Yes.
ma'am. It will be just that resonance frequency calculation, else every part will be same.
Every part, because VRMS will be same, because peak to peak will be at 10 volt only. So accordingly, that will be 3.535 VRMS only. Then whoever changes the capacitance, then accordingly inductance will change. So
Yes,
in
ma'am.
that case, if we change the frequency, we will have to just calculate it by that 1 by 2 pi root LC. So nothing else will be changed, ma'am.
Okay, okay. Okay, fine. What is your roll number, Ankush?
10026, ma'am. Can I stop presenting, ma'am?
Yeah, please.
Excuse me, ma'am.
Yes.
Thank you.
Ma'am, I have also done at 500 hertz. Should I change the frequency or leave it at that only?
No, no, just leave it at that only.
Okay, ma'am.
Never present. Yeah.
Thank you, ma'am.
Ma'am,
Yes.
is my screen visible?
Yes, yes.
Ma'am, this is the experiment 3. So, ma'am, I have taken 500 hertz only. And assuming the value of capacitance, I've calculated the inductance.
Hmm.
VRMS was calculated by taking VPP as 10 volts and
Hmm.
by the formula of VPP divided by 2 root 2. And here, ma'am, 1 minute. Ma'am, this is the graph that I'm getting.
Okay.
And ma'am, frequency
This.
response I got out to be 520 approx. 1 minute.
Okay.
Ma'am, 504.
Okay. Fine.
Ma'am, and experiment 2 was left in my part.
Hmm. Present that also.
Yes, ma'am. Ma'am, this is for RC much greater than T.
Okay.
It's just like a wave type, ma'am.
Hmm.
Ma'am, RC equal to 2, it was just on the zero line. It didn't move.
Why you are getting this kind of response? This is for RC greater than T.
No, ma'am, this is for RC equal to T.
Okay,
For
equals
greater than
to
T,
T.
it will be wave, ma'am,
Yeah,
because
yeah,
it
yeah,
will
yeah.
it will
Okay.
vary.
Okay. Yeah, show me for RC greater than T then.
Ma'am, I showed you for RC greater than.
You have earlier shown me only experiment number 1.
Yes, ma'am. I have shown you experiment number
Okay.
1, now experiment number 3, and now I am
Number
showing you 2.
2. Okay. Okay, for RC less than T.
Yes, ma'am. Ma'am, for RC less than, I have this doubt. For RC less than T also, it's coming out to be on the 0 line only. It's not changing. And for equal to T also, it was coming on this.
Why? So how much frequency you have taken?
Scale, I think we need to
Uh,
change
Changing the scales
the
per
channel is.
division, we can enlarge it, ma'am, I guess. Because
Yes,
for
ma'am.
me,
If
it was
if it changes the scale, then it will enlarge. I think the
Okay,
graph
please
is
change.
fine.
Please change your scale. Then show me.
okay, ma'am. I'll change it and show.
Yeah. Okay. Next one is Shashank.
Ma'am, did you note my roll number?
Yes.
Okay, ma'am.
It is 38, right? 10038.
Yes, ma'am. Shashwatra 1003. Yes, ma'am.
Yeah, Shashank, please.
Yes, ma'am.
start
1 minute.
presenting.
Is my screen visible, ma'am?
Yes.
Ma'am, this is for the third experiment.
Mm.
And they have asked us like to perform two experiments, like aim 1 and aim 2. But since we can observe second aim in the first itself, like through frequency response plot.
Mm.
So I have done only one, ma'am.
Okay. I
And
have
have
taken 1 kilohertz frequency.
and 10 volt peak to peak, and
Okay.
C1 and L1 we can calculate from that.
Mm. Mm.
And ma'am, resonant
You're
frequency is at 1
getting
kilohertz,
exactly
and
1 kilohertz.
yes, ma'am,
Okay.
we can
Okay,
change the
fine.
value using the formula. I guess it would be the same.
Mm.
Using this 1 minute.
So, okay, that's fine. Have you shown me last 2 experiments?
Yes, ma'am, I have shown you experiment number 2
What is the
as well
roll
as
number?
ma'am 212, 212.
212. Okay, yeah. You have shown me first 2 experiments.
And ma'am, experiment number 4 also.
You have also done that? Okay.
Yes, ma'am, I have only done one aim of it because the second one I don't know the concept, so I did not try it yet.
Yeah.
And,
Wait a minute. Then I have to go through that experiment also. Wait a minute. It is design the shunt positive clipper. So which
yes, ma'am.
circuit you have completed?
Ma'am, I have completed for the shunt positive, shunt negative series, positive series,
Voltage
negative.
source is connected. Negative series and positive series.
Yes, ma'am. Our negative clipper and positive clipper.
Yeah, negative flipper series and negative positive flipper series. Okay.
Yes, ma'am.
Yeah. Show me.
1 minute, ma'am. Yes. So, ma'am, the red one is the input line and the blue one is output. Here I have taken 0 volts as the reference. So
Just show
my
me the
output,
output only.
this is the output, ma'am. Only output, only.
Yeah, only output. Because it is overlapping, so it is very much difficult to identify
Yes,
which
ma'am.
one is the output.
Ma'am, I have taken 0 volts as the reference here. So the maximum voltage will be 10 minus
Hmm.
that. So it is
Okay.
9.226 as seen here.
All right.
And 1 minute, ma'am. I just forgot to show you this, the transfer characteristics. Ma'am, the transfer characteristics can be seen here.
Hmm. All right.
And this is for negative.
Okay.
And should I remove the input signal or should I just keep it, ma'am?
No, it's okay. It's okay. I can see it. Okay, it is negative clipper and transfer characteristics also.
Yes, ma'am. 1 minute. Yes, ma'am. So the transfer characteristics.
Okay. Okay, fine.
And this is shunt positive and shunt negative. This is shunt negative. And yes, ma'am. This is the output waveform and transfer characteristics is here.
Hmm.
This is shunt positive. Transfer characteristics and the output waveform.
Okay.
Yes, ma'am. I'll just try the next time also. I don't know the
Yeah.
concept, so
No, you have already done. You have done with zero reference, right? Series and shunt both.
yes, ma'am. 0 reference. That is this one I
Okay.
have tried it, ma'am. This one I got it. Like it basically shifts it 2 volts above.
Yeah.
But they
Yeah.
have talked
Because
about double
whatever
shunted.
whatever reference voltage you have applied, your wave will be shifted to that voltage, above
Yes, ma'am.
or lower. Okay. So that is the concept. What you are not getting?
Another there was double shunt, double-ended shunt, I
Yeah,
guess. Yes.
exactly. So in that you have double shunt, right? Means two reference points you have, VR1 and VR2. Okay.
Yes, ma'am.
So what will happen? Your both means positive as well as negative side of the wave will be clipped. So one side will be clipped by VR1, means the reference will be VR1 for that, and the other by VR2.
Okay, ma'am.
You can just see this waveform which is given by the side of this. Here 2 volts you have applied as reference voltage, and suppose the zero point 0.6 is the drop across this diode,
Yes, ma'am.
right? So for positive clipping, your wave will be given at 2.6 volts. After that, your this signal will be clipped, and in negative also the similar thing you can see.
Yes,
Are you
ma'am. It
getting
is
this?
clipped. Yes, ma'am.
Yeah.
Okay,
So
ma'am.
this drop across this VR1, that is 2 volts, plus the drop across this diode D1 and D2.
Whatever. Yes, ma'am.
Okay, so that is around zero point 0.6 volts. Here they have assumed as 0.6 volts. Okay, so total 2.6 volts is the drop across this whole parallel line, right?
Yes,
So
ma'am.
your this input signal will be clipped because you can see the direction of diodes is opposite in both. So one is acting as a positive clipper and other is acting as a negative clipper.
Okay, ma'am. So it is just derivation of from the above one, like here.
Yes, exactly.
Okay, ma'am.
Okay, they are the shunt clipping. They are doing the shunt clipping for negative as well as the positive.
Yes, ma'am. Ma'am, this is the experiment number 2 that came. I just tried it, but yes, ma'am.
Okay, fine. So you all are also preparing your this
Yes, ma'am.
lab notebook.
Yes, ma'am.
Okay, so you may please send your lab notebooks of last two experiment to me.
Okay, ma'am.
All right. So will you be uploading it here, or you will be okay? Don't upload it here. You may send it on my mail ID.
Okay, ma'am. Yes, ma'am.
I mean, file section we
Okay.
can, if you want.
We can upload it in files also.
Actually, in file section, what will happen? The others who have not done, they will just copy.
Then, ma'am, you can create link also, no, in that section only. That individually we can upload it.
Okay, then yeah, I
In that it
will.
is not. In that it is not visible. That
Yeah. Okay, fine. Then I will be sharing a link. You may upload it there. Okay.
yes, ma'am. So, ma'am, please
Okay,
give it a
Shish.
day or
Yeah.
2 day time so that we could make the file. Actually, we have
Okay,
not.
fine. Okay, fine. No problem. You may complete up till experiment number 3,
Three.
and you
Yes, ma'am.
may submit it by Saturday.
Okay. Yes, ma'am. Yes. Sure.
Okay. By
Yes.
Saturday, you may upload.
Yes, ma'am.
Okay, Shashank, what was your roll number?
Ma'am, 212,
Okay, yeah,
212.
212. Wait a minute. Okay, next one is Harshvardhan. Yes.
Ma'am, I have completed the fourth one, ma'am. Can I represent?
Yes.
Ma'am, is my screen visible, ma'am?
Yes, it is.
Ma'am, here the first one is, ma'am, negative clipper with zero reference, ma'am.
Mhm.
And ma'am, this is the output here, ma'am. Ma'am, is it visible, ma'am, here the graph?
Actually, graph is not visible.
Okay, ma'am, 1 second.
Yeah.
Ma'am, now
Actually, screen is stuck. Can you
screen
please
is,
stop and share it again?
yes, ma'am. Ma'am, now is it visible, ma'am?
Wait a minute. No, I can see only black screen. Yeah, now it is. Okay.
Now
Yeah.
it's,
Yes,
ma'am,
yes, yes.
so first I'm showing negative clipper, ma'am, series clipper
Mm-hmm.
with zero reference, ma'am. And this
Mm-hmm.
is the circuit. And ma'am, for this, I'm getting this as my out. This blue one is as my output, ma'am, and red as my input, ma'am.
Okay.
And this is the transfer characteristics, ma'am.
Okay, fine.
Ma'am, now it's this one is positive clipper, ma'am, with zero reference, ma'am.
Mm-hmm.
This one,
Okay.
ma'am. This is the transfer characteristics, ma'am. This is the next graph, ma'am. Ma'am, this is also positive clipper, ma'am.
Mm-hmm.
Ma'am, this is shunt one, ma'am, shunt. And ma'am, this is
Okay.
the transfer characteristic for it,
Hmm.
shunt clipper. Ma'am, this is negative shunt clipper, ma'am. This is the characteristics, ma'am.
Okay.
Ma'am, this is the transfer characteristics.
Okay. All right. Have you done the second part also?
Yes, ma'am. Ma'am, in first one also some of them were left circuits, ma'am, and this one is there, ma'am. Here also clipping is being done, ma'am. It's ma'am. These are with reference, ma'am. That was without reference,
Hmm.
ma'am. This one I'm doing
Hmm.
with
Hmm.
reference.
Hmm. So this is positive flipper. Okay.
Positive flipper, ma'am. Ma'am,
Fine.
this is my transfer characteristics. Ma'am, this one is ma'am. Here also it is positive clipper, ma'am. But ma'am, here I had a doubt, ma'am. This one.
So why
I did the circuit, ma'am, but I had a doubt here.
it is again positive flipper, right?
Yes, ma'am.
But it
Like
should
what?
be the negative. What?
Ma'am, what is the difference between this and this, ma'am? Like output
No,
difference.
no, no. This should be the negative flipper.
Ma'am, negative clipper I did here, ma'am. This one is the negative clipper.
Okay.
This is my transfer characteristics, ma'am.
Okay, with reference. Okay.
And ma'am, this is my for the second name I got this as my graph, ma'am. Here positive and negative both side I'm getting
Negative both. Okay.
this, ma'am. And this is my transfer characteristic, ma'am, for the same.
Hmm.
Ma'am, can I stop sharing, ma'am?
Yes.
Ma'am, is it visible, ma'am?
Yes.
Ma'am, this is I'm getting.
It is around 101. One, how much it is? What is the resonant frequency?
Uh, Ma'am, it's about 9.31. At this we are getting.
You have initially taken 200 hertz, right?
Yes, ma'am.
Then how you are getting it in kilohertz?
Mm,
That means you have not designed it properly. Okay, your theoretical value and your practical value should be same, right?
yes, ma'am.
So if you have taken the how much resonant frequency you have taken theoretically?
Ma'am, the initial frequency that I've taken, ma'am, that's at 200 hertz.
Calculate the resonant frequency.
Just a
Is
minute,
it
ma'am. May I
showing
show
the
you again?
resonant frequency?
What, ma'am?
How you have calculate the values of capacitor and inductor?
Ma'am, for the ma'am resonant frequency, ma'am, XL barabar XC, and from there, ma'am, like omega equal to 1 by under root of LC, ma'am. From there, we can find out the resonant frequency as a theoretically.
No, no, no. How you have designed L and C? See, the resonant frequency is equals to 1 upon 2 pi under root LC, right?
Yes,
And
ma'am.
then you have to choose one resonant frequency. Then you have to choose either value of inductor or the value of capacitor. Suppose you have chosen this capacitor as 1 microfarad, right? Then from that formula of resonant frequency, you have to calculate the value of inductance or the inductor. Okay, value of L you have to calculate. That is how you will design this RLC circuit. R is already given as 100 ohms. You may take another value, but suppose it is 100 ohms only. So for resonance, value of R does not impact our circuit. Okay. For at resonance, whatever value of R is there, it does not depend on the value of R. Okay. It only depends
Yes,
on the value of L and C.
C.
Okay. So first you assume resonant frequency something, then assume value of either L or C, and then calculate the other one. If you have assumed value of C as 1 microfarad, then calculate L, or if you have assumed this inductor value as 1 Henry, then calculate value of C. This is how you have to design it.
Okay, ma'am,
Got
give me
it?
2 minutes. Yes, ma'am.
Okay, Vinamr, start
Yes,
sharing,
ma'am.
Vinamr.
Yes, ma'am, sure.
And today we have to do only third experiment now. Fourth we can share. We can show it next class, right?
Afterwards, yeah.
Thank you.
Ma'am, is it visible?
Yes, it is.
So, ma'am, for a resonant frequency, uh, that is my resonant frequency is 31.14 hertz, and I have assumed my inductor's value to be 1 Henry, and accordingly, I am getting my this voltage plot and frequency plot.
Okay.
So that's around 31 only. So that is my third experiment.
Okay, fine.
And my first experiment, I couldn't show it in the first class. So
Hmm.
and this is my first experiment, half high pass circuit.
Low pass filter. First experiment is low pass filter.
So this is for RC much larger than T.
Hmm.
This is for RC equal to T.
Hmm.
And this is for RC much less than T.
Okay.
And the second one is high pass circuit. So
Hmm.
so this one is for RC much greater than T.
Okay.
This is for RC equal to T. And this one is for RC much less than T.
All right.
And ma'am, fourth
Okay, what is
experiment,
your
I
roll
am
number,
currently,
Vinam?
ma'am, 270.